Just Z, be ready to ask a question and go next. It's not fixed, it's fixed. I don't know, that just looks more grammatical to me, I don't know.
Okay, start.
Okay.
Okay, so good afternoon. Today I'm going to talk about the Paul theorem. To motivate this, imagine we are holding a map of Columbia campus. We have a map and walking in the campus, and then suddenly the map is fallen to the campus, and this is the actual campus. So an interesting phenomenon concerning this process is that we can find a unique point in the map, such that when the map falls on the campus, this point will coincide with the same location that it corresponds to. So, okay. So to prove this, let us call this operation T. And T is an operation, we think of it as an operation from the map to the map, where we identify the image of point P back into the map. Say if X is a point and we drop the point corresponding here, then Tx will be the corresponding point on the map. Okay. So what is the claim? The claim is that we can find a unique point P such that Tp equals T. So in order to prove this, let us first observe a key property of this operation T. Key property. Okay. So let us look at 2 points, X and Y in the map, and look at the corresponding image Tx and Ty. And because the map is much smaller than the actual campus, the distance between X and Y is larger, much larger than the distance between Tx and Ty. And we may assume that this distance is larger than 10 times of this distance. And we can write in this way: Tx minus Ty is less than 1 over 10 x minus y for all points X and Y. Okay, so let us prove this claim. So we will divide the proof into 2 steps. So in the first step, we will construct a sequence on the map, a sequence Xi of points on the map, such that this sequence converges. And secondly, convert to a point X. And secondly, we will show that this point X is the desired point that we want, which is that Tx equals
Say
X.
that again, this point X is the
Desired.
desired, okay.
This is the desired point that we want.
Sorry, you mean the T is a function without any restriction?
Not a restriction. You can deduct a mapping from this map to the map. It takes the
So
point.
it's continuous or
Yes, it is continuous.
it's continuous?
Yeah, this condition shows that it is Lipschitz, so it is continuous.
But I think the difference between Tx and Ty is smaller than the distance in the map.
Yes. Because we identify Tx back to the point. Therefore, it is smaller.
Yeah.
And by this property, it is continuous, so it is fine. Okay, so let's prove the first step. So let's go over the first step first. Okay. So let us define a sequence in the following way. So first, we take a point x0 on the map. Say we pick a point here, x0, and then we define iteratively the sequence xi equals tx minus I for I equals 1, 2, 3, and so on. So what does this mean? So say x0 and then x1 corresponds to the image of x0 and so on. So this is the sequence that we define. Okay, so first we will estimate the distance between adjacent points, which is I plus 1 and si. So first we estimate this distance. So using the property and the definition of the sequence, we have this. So the xi plus 1 minus si equals txi minus tx minus 1. So which is more than 1/10 xi minus xi minus 1. And then we can iterate this process and get this inequality. So we see that the distance between adjacent points is controlled by this term. And this term is getting smaller as I is getting larger. So the distance of this will decrease. And secondly, let us first fix a point xi. And then we want to estimate the distance between xi and its later point. So let's take fj, which is bigger than I, and then we look at the difference between xj minus xi. So in order to use this estimate, we will write it in this way. We will first subtract xj minus 1 and then add back xj minus 1 and so on. And then we can use the triangle inequality to get this.
Wait, can I ask a question, Aaron? So xj minus xj. No.
J minus 1.
Yeah. I don't understand why you are subtracting xj minus 1 and then adding xj minus 1.
Because we want to use this previous estimate to estimate this distance. And this is an estimate regarding adjacent points. So the index has difference of 1. So we want to.
But it just looks like if you subtract something
and
then add the same amount again, what's the point of that step?
So we are actually doing nothing here.
Okay.
So that's why we have equality sign.
I see.
But after we write it in this way, we can use the triangle inequality. So we can put this and this together.
Okay.
And then we can break it into pieces. And then we get this estimate. Okay.
Is that a little r? xj minus
2.
Oh, 2. Okay.
Yes. So after doing this, we can use this estimate, and then apply this estimate into each of these terms, and we get this. So we can factor out this coefficient, and after some algebra, this is what we get. Okay. So we know this distance is controlled by this term. So there is a special property in here because this upper bound is actually independent of j. So this means that if we have xi here, and j is later point, and the distance between it is strictly contained in a circle of radius of this, which depends only on I. Therefore, all of the later points of xi is contained in this circle. And also, we further observe that this band here actually depends on I, and when I gets bigger, it gets smaller. So say we first have a Si, and then we pick a later term xj, and all of the later term will be restricted in this smaller circle, and so on and so on. And we can see that this circle actually will shrink to a point. Therefore, this justifies that this sequence xi converges to a point, say x. So we prove the first step. Okay. So we will write this convergence formally as limit I to infinity xi equals x. So let's we will claim that this x is the desired point. So what we will do? We will simply take limit on both sides of this equality.
What is Li? Is that say lim?
Limit. It depends.
Limit.
Limit.
Okay.
So we write this convergence formally as in this way. Then we take limits on both sides. So this gives us this. And we can put the limit inside the bracket. Because this sequence converges to x, this equals x, and this equals dx. And therefore, x is the point that is fixed by t. And finally, we have to claim that we have to show that x is the unique point that satisfies this property. So, to prove this, let xy be 2 points such that Tx equals x and Ty equals y. Then xy equals Tx minus Ty. Then using the property satisfied by t, this is smaller than 1/10 x minus y. Because because x minus y absolute value is non-negative, this means that x minus y is 0 and x equals 1. This means that x and y are actually the same point. So x is the unique point that satisfies this property. Okay, so this is the end of my presentation. Thank you.